Thank you. So this morning I was wearing, as Swami says, my foundation hat to give the keynote. I'm going to switch hats now and wear my Bluespec hat and talk about RISC-V's RISC-V verification design tools. So first of all, a little bit about Bluespec itself. Many people have asked me already, what is Bluespec, where is it, what does it do, etc. We're actually not a young company. We were founded in 2003, and it's originally a spin-out from MIT based on technology that was originally developed at MIT, but then developed at Bluespec since then. We are headquartered in Framingham, which is maybe 20 minutes from here, 25 minutes from here, west of Boston. So our core technologies and expertise are really in, first of all, and this was our founding technology, is in high-level hardware design. So you heard earlier Adam mention Bluespec in his talk. That's the language that has its origins in research in MIT and then developed at Bluespec, which is a very high-level language. And I'll say I have a final slide today in which I will be talking a little bit more about that. And the emphasis is shifting a lot more nowadays to processor system design and verification tools. So our customers, we have various customers in quite diverse set of markets, major semis, cloud providers, and so on. We also provide our tools free to universities. So there's lots of universities who use our tools. You heard also in Adam's talk today that MIT has re-architected their intro digital design course to use our tools. You'll find quite a few top-tier universities around the world using our tools. So turning attention specifically to RISC-V, which is the topic of our gathering today, we've been involved in RISC-V since about 2013. So I think from Krista's slide you saw that the whole RISC-V activity started in about 2010 in Berkeley, and as their activity solidified and they started teaching courses and the stuff became available on the web, the word spread, and then around 2013 is when March 2013 or February 2013 is when I remember first creating a simple RISC-V processor using Bluespec. And we've been working with RISC-V things ever since then. So we are one of the founding members, a platinum founding member of the RISC-V Foundation. Charlie Hawk is our CEO. He's a board member of the RISC-V Foundation. And I myself chair one of the task groups, which I mentioned before also, which is the ISA Formal Spec Technical Group. So we're not competing in the market in terms of cores per se, but we like to contribute cores to the open source community, and there are 2 open source cores out there already on GitHub, and there'll be more on the way, and I'll say a little bit more about it in a second. So here's the plan. My plan for today. I'm going to mainly talk about this product that is coming out within about 6 weeks or so, called the Bluespec Innovation Factory, or at least the first version of it is coming out in about 6 weeks. And most of my time I'll just be talking about that. I'll also mention the open source cores we have, which are called Piccolo and Flute. And then I'll say a little bit about the high-level design language. So here's what the Innovation Factory is trying to address. You've heard about lots of open source cores out there from many different places. And let's say you're a chip designer who wants to use one of those cores. It's quite a daunting task. So as the famous aphorism says, in theory there's not much difference between theory and in practice, but in practice there is. So so the problem is first of all, these cores are all over the place in many different locations and sources. You have to go research each one of these. For each one of them, you can download it, but then there's a whole bunch of prerequisites that you'll have to install in order to get anything running at all. And if you're successful getting through all of that, you might have a core. You also have to build tool chains for the particular version of the core, because most of these cores are highly parameterized, so you're picking a particular instantiation typically for your uses, etc. Then you have to build, then once you have the core itself, even if you successfully produce the Verilog, what are you going to do with it? To simulate it, at least you need a system around it, some memories, maybe some IP devices, etc. So there's an integration into hardware and software stacks. That might be, simulation may be too slow for you, so you may want to run on FPGAs to get simulation at speed as you're evaluating the core part of it, and then finally, once you're satisfied with things, there's a lot of further verification if you're going to go on to ASICs, etc. So the problem is a lot of this is hand-built blood, sweat, and tears in most places. And what we're trying to do is to give you an out-of-the-box solution so that on day one, all of this is ready for you. And then you can just focus on the cores that you're looking at, exploring what variations in the cores you're going to play with, etc. So this Innovation Factory product is, again, being agnostic about where the cores come from. And so up here you're seeing a variety of cores named, and there are many more out there. Rocket is the most famous one that came out of Berkeley and is also used by Sci-Fi, for example. Piccolo and Flute come from us. Pico RV32 comes from Clifford Wolf in Australia. Polpino comes from ETH in Zurich. Swerve is the open source core that Western Digital announced last December. Boom, like Rocket, also comes originally out of Berkeley. And RISC-V was mentioned earlier today, comes out of MIT. So the idea is that you can get any of these, and then what we will provide, first of all, is a system around it so that you can just directly plug in the core of your choice here and start running things out of the box. You can start running application software, you can compile your own codes, etc. And while you're doing that, you can be doing simulations. We'll give you pre-built tool chains. So that is another issue. You have to build your own GCC, you have to build your own GDB, you have to build your own OpenOCD, etc. All of that comes pre-packaged for you in this thing. And you can so immediately start evaluating the core you're choosing and the variations of the core you're playing with from this catalog of cores and start evaluating it. So everything is available immediately for simulation. If you get the FPGA emulation add-on, you can also then immediately start running on FPGAs. We provide pre-built bit files for you for various particular choices of core configurations, and we can generate new ones if you need it. If you're going to the ASIC level, you need further verification of components, subsystems, etc. There's a logic verification add-on. And then finally, for some customers, you're adding accelerators also. So these systems will come with extra slots where you can plug in your own accelerator. So you can then, and we provide all the infrastructure needed so that you can easily plug it in and immediately start working with it. So conceptually, this is what it looks like. Physically, this is what it'll look like. You will actually get a box, which is a small server, which is basically an Intel NUC server that has been pre-installed and preloaded with everything I just said so that you can run these things out of the box. It'll have a catalog of open source cores, some from us, some from others. It'll have an IP system surrounding it that is based on Xilinx IP basically, and complete the software setup for that, the tool chains, operating systems, and so on. And you're basically just sort of configuring exactly what you want from that, and you immediately get a running system that you can build on this. And if you do the FPGA add-on, then you can also just immediately run it at speed at FPGA. So basically the idea is that no installation issues, just add your keyboard, mouse, and monitor and start running on day one. So this is the basic product which we're calling the Innovation Factory. The first version of this is going to come out in April. Early versions of this are already out there with some of our early adopter customers and some of our research partners. So we already, it's not just in development, we're fleshing out a lot more breadth and depth in this. So we will start with Rocket, Piccolo, and Flute, and RISC-V as the, and also Boom, I think, as the main initial catalog of open source cores that we'll be able to plug in there. And over time, we will just keep expanding that. Now, as you've heard, each of these is actually a generator. In other words, they're highly parameterized, and you can choose a particular profile of parameters to generate a particular instance of it. So, of course, combinatorially, that's a very large number of things. We will be providing a large number of pre-generated cores like that with particular choices. But, of course, if you talk to us, we'll be able to generate for you other variants of it. And they will all just go back into the catalog. And you get the whole catalog as part of this thing, so that you can choose which kind of core you might want. So, so the first version, like I said, will come out in April, and over time it'll be expanding to do a lot more cores, getting into multi-cores, etc. We'll probably have different versions of the FPGA emulation platforms and so on. So that's about the central product of the company moving forward, which is this innovation factory. Let me talk a little bit about the open source cores that we have. You see the GitHub links out there. You can go there and find them and download them if you like. They're small at the moment. There are more coming on the way, which are going to be larger and more sophisticated cores. And so these are, as you can see, they're 3-stage in order, 5-stage, etc. Both of them have the same capabilities as listed in these bullets. So first of all, they can do all the basic, the standard instruction set extensions of RISC-V, RB32 and RB64, M, A, F, D, C, all 3 privilege levels, machine, supervisor, and user with virtual memory. And they're completely parameterized, so you don't have to use all of these. These are just compile time flags in how we generate them. So you can omit whatever you don't want from this. I like the word iterative subtraction that Krista used. Similarly, you can choose just the pieces you want, and we generate the core with just those components in them. And there are more parameters here that I haven't mentioned. They have separate IND memory channels and L1 caches, optional MMUs. All of them configurable in various ways in terms of sizes, associativities, and things like that. So everything is optional. The other thing that they come with is a standard debug module. So within the RISC-V Foundation, one of the task groups has standardized, and this has been ratified as a standard debug module, which is a gadget that basically sits very close or inside the CPU. And on one side of it, it has ways to reach into the CPU to be able to certainly read and write state, registers, CSRs, memory, etc., and also run control. So you can do single stepping, breakpoints, those kinds of things. And on the other side of it, it speaks a standard protocol called DMI, Debug Module Interface, for which we already have, meaning what? The community already has connections to OpenOCD, which in turn connects to GDB, so you can debug things from GDB in the standard comfortable way you're used to using GDB. So those already exist in Piccolo and Flute. They also exist on the Rocket core. For other cores, it's a task of integrating the debug module appropriately if it doesn't already have a debug module. So you can imagine some new cores might initially come on without that, but over time they'll gain the debug module as well. Also, these cores include the PLIC, the platform level interrupt controller. So this is again a highly parameterized interrupt controller which are essentially have 3 kinds of parameters, one is the number of sources that can generate interrupts, depends on how many devices, etc., you have in your system. It's parameterized on number of targets, which for a single core is essentially 2 targets. You can deliver interrupts either at machine or at supervisor level. In potentially 3, machine, supervisor, or user level. But when you go to multi-cores, it gets multiplied by one such set for every core. So that's the parameterizable number of targets. And the other kind of parameter is the number of priority levels you'd like to support for interrupt. So we generate the hardware for that. The PLIC is a memory mapped gadget. So these questions of, so the CPU through the memory mapped interface can interact with the PLIC both to enable, disable interrupts, etc., and also to liaise with the PLIC about accepting an interrupt and clearing the fact that you have an interrupt. So this becomes more important once you have multiple targets and multiple cores where the interrupt may be available and visible to multiple cores, and you want to have atomically it delivered to exactly one of those cores. So this is what all of these already exist in the things that you see up there on GitHub. So my final thing I want to talk about is a little bit is the BSV high-level hardware design language. You've heard it mentioned certainly in Adam's talk and maybe also a little bit in Morley's talk earlier today. So this has been Bluespec's core competence for more than a decade now. It's a language that has its roots in formal specification languages and functional languages. So if you think of languages, the sort of umbrella category we refer to is term rewriting systems, or you might have heard it under the name rewriting rules. And it's very popular amongst people who are trying to formalize highly concurrent systems because rules are a way of expressing behavior without committing to any kind of sequencing. It's a reactive state, reacting to the current state, some activity happens. So this is an excellent model for dealing with hardware, etc. So historically, it had been used for modeling and typically software, but also to some extent hardware. And the original research at MIT that spun out into Bluespec found a way to take that very high-level abstract computation model and synthesize Verilog, synthesizable Verilog out of it, so that rather than having to use it just as a verification mechanism against handwritten hardware, you can actually just directly generate the hardware out of it. So this is basically what the language itself is. We like to think of the language as open. In fact, about 8 years ago, we offered it all to the System Verilog committee as part of the System Verilog standard. But we were midgets compared to the giants in the room. So needless to say, it was not a high priority for others to accept it, so it didn't get accepted. But anyway, that's just a demonstration that we're happy if other people wanted to go and implement the language, etc. So our implementation of Bluespec is a compiler that takes designs written in BSV and compiles it into basically vanilla RTL. And as Krista also mentioned earlier with regard to Chisel, it's machine-generated Verilog, so it's very clean, very structured Verilog. It has never given us any problem with any downstream tools, whether it's simulation or synthesis tools going beyond that point. So it's a scalable industrial strength language. So it's, as I said, given its provenance of more than almost 2 decades now out there in development, it's gone through a lot already, and it's very well documented and very stable. So you get full support from Bluespec when you use BSV. It's most recently been used in a chip that I'm told is 1 billion transistors. So that would be the largest one. And when I say major cloud provider, you could probably fill in the gaps as to who that might be and what application that might be. Earlier, it was used as a direct replacement for Verilog or System Verilog for IP subsystem design. And the two ones we're able to talk about are one from TI and STMicro. TI used it in their OMAP chips for the video and graphics controllers. So the first Amazon Kindles used TI's OMAP chips, and the video and graphics controllers there were designed in Bluespec. STMicro has used it for high-speed and complex video data movement and manipulation in their set-top boxes. So it's interesting also that while it's a hardware design language per se, and so people are designing hardware with it, both FPGA and ASIC hardware, being high level, it's also very useful for designing verification IP that will synthesize and run on FPGAs. So for example, nowadays people for verification might use system error log, where they use things like object orientation and things like a UVM methodology, etc. But unfortunately, that's not synthesizable. So when you're trying to run FPGA-based verification or emulation, you still have that test bench sitting on the host and your IP sitting on an FPGA or a custom emulation machine. This allows you to actually move that stuff over into the FPGA itself. So at least 2 top 10 semis are using us for that purpose, not for chip design, but as high-level, flexible, agile verification IP generators. And the other use I should mention is that many people in the very early stages of design do architectural models of things. So if you're designing a new processor, you might, for example, use the GEM simulator, which is a detailed pipeline simulator that can give you cycle counts and power estimates, etc. The problem is when you are modeling microarchitectures at that level of detail, your simulation speed drops like a rock, and you can't really do large-scale simulations there because it's just too slow. So here again, the idea that it's a very high-level language which can be used like an object-oriented software language, the terminology that Adam used a little earlier, allows people to write those models instead of writing it in C++. If you write it in BSV, you can actually synthesize it and you can run them on FPGAs. So it's been used as a very high-level architectural modeling language as well. Many different uses that we hadn't anticipated. Originally, we were just thinking of it as a high-level IP hardware design language, but you can see both the verification side and the modeling are serendipitously new uses that came out of this. So we actually do all our own designs in BSV. So in fact, both Piccolo and Flute are written completely in BSV. So if you'd like to take a look at what the language looks like, well, one is if you go to this website, you'll find the reference manuals, tutorials, and those kinds of things. So you can see things over there. But if you go to the GitHub Piccolo or Bluespec Flute website, you can see how a RISC-V design is done in BSV. And so I will stop there. I've talked about 3 different things today, which are, one is the sort of core product focus of the company, but I also wanted to tell you about other things that we're doing in the RISC-V space. The Innovation Factory is for people who are thinking about doing a new chip and they're trying to evaluate which of the open source cores they want to use and in what configuration would they like to use it. And normally it would take you months or a year of blood, sweat, and tears to get it all together before you can even start your evaluation. This is trying to get you started on day one with pre-built, pre-compiled, pre-software tool chain generated, everything up and ready for you so that you can just push a button and get started on that. We've contributed so far two open source cores to the RISC-V community, and those of you who are interested in actually doing design in a high-level hardware design language, this might be of interest to you as well. Thank you.
Thank you. We can take a few questions, then we can go for a break. So this Innovation Factory is like an emulation platform, like it's different. Like EDA tools have emulation platform like Palladium, Cadence. It's similar to that, or it's different?
Well, yeah. So the question is the Innovation Factory an emulation platform? In a way, yes. A couple of points. One is this is specialized just for a RISC-V system evaluation.
Correct.
So emulation is sort of a general purpose terminology. The second thing is things like Palladium and things are actually custom design hardware, and they're very expensive. They're $500,000 and more, big box things. But even in that industry, emulation industry, all the big three, Cadence, Mentor, and Synopsys have now, they still do those emulation platforms also, but a lot of it has moved into FPGA-based emulation. Essentially, roughly about, I would say about 10 years ago, FPGAs became capable enough that they could start eating into that emulation market. Before that, emulation was only done on those big boxes. About 10 years ago, the FPGA capacities and tools reached the point where you could seriously move some of that off into much lower cost off-the-shelf FPGA emulation. So in that sense, yes, but it's all specialized. We're not trying to give a general purpose emulation capability. We're saying we're going to give you an emulation for a pre-built RISC-V SoC system with, a catalog of open source IPs that are pre-built that will run on that. So the purpose of the FPGA thing is speed, just speed, compared to just doing it in simulation.
And if somebody gets a box, if the new open source cores get added, they can add them virtually, or you have to get a new box again? It's the same box can add.
Okay, that's a business model question. I'm not quite sure. I think our intent is that you just get the whole catalog, and if the catalog improves, you just get you get that as well. So, but the issue, there is an integration thing, and we're going to be the blood, sweat, and tears that a customer would have to go through if they did it themselves is indeed in integration. If I get a new open source core, how do I build everything around it so that I can even start running a piece of, even the smallest piece of code on it? And this is something that runs out of the box, and we are doing the integration for you so that you can say, oh, I want to use, this particular variant of Rocket, I want to evaluate it. You just plug it in and it runs. You just pick it out of a menu and it runs.
I see.
It runs. So we're essentially going through that earlier phase of integration into the whole system so that it runs out of the box.
I see. Very good. Any other questions?
Okay, thank you very much.